When we say opposite, we really mean additive opposites. So the expression A and the opposite of A are additive opposites since they add to zero. So two numbers are additive opposites of one another when they add to zero. So let's go down here and get the additive opposites of these three numbers. You will often hear me just say opposite rather than additive opposite, but additive opposite is what's meant when I say opposite. So what's the opposite of -7? Well, the number you can add to -7 to get 0 is +7. Those two are additive opposites. The number that you can add to 5 to get 0 is -5. So 5 and -5 are opposites. And the opposite of -43 is +43 because they add together to give you 0. So as you can see, opposites can be either positive or negative. Hence the reason the expression opposite of x can represent any real number, including positive numbers. In the previous example, we saw we got +12 rather than -12. So what can you do to each of these numbers to get their corresponding opposite? While you can add 14 to -7 to get 7, adding 14 to 5 does not give you -5, and adding 14 to -43 does not give you 43. The thing that you could do to each of these to get their corresponding outputs is multiply by -1. So how do you get from any number to its opposite? That's the same thing as multiplying by -1. So multiplication by -1 gives you opposites. This implies that the opposite of x is the same thing as x times -1. When you multiply by -1, you get the object's opposite. Let's now summarize some of the prerequisite knowledge that we've been building in order for us to fully understand how combining like terms works. So, first one here, adding a positive number and subtracting a negative number are equivalent. So here's just a couple of examples. You subtract -5, that's the same thing as adding +5. Or this could also be as a variable expression. So x minus -5 is the same thing as x plus 5. So adding a positive number and subtracting a negative number are equivalent. We also saw that adding a negative number and subtracting a positive number are equivalent. And here are two examples, one fully numeric, one with a variable expression in it, that demonstrate what we mean by adding a negative number and subtracting a positive number are equivalent. We also saw that subtraction takes place between two mathematical objects, meaning if you look at this expression right here, this is not a subtraction sign because there is no mathematical object up here. This is a subtraction sign. The first minus sign is a negative sign. Then we also saw that negative signs may represent negative numbers or the opposite of an expression. So we introduced the idea of an opposite of an expression. So in this one here, the 3 is negative. This is a -3. However, this does not necessarily mean you have a negative number, as we've seen in the previous slide. Opposite of x could actually represent a positive number. And then finally, as we saw here, to get the opposite of a number, you multiply it by -1. Whether that number is positive or negative, to get its opposite, you multiply it by -1. Let us now revisit the original algebraic expression we used to start this discussion about combining like terms. So originally, we said that this expression can be written in a much simpler form. But to review some of what we've done here, I don't want to still yet write it in its simplest form. We need to go over some additional things. I want to first just answer some of these questions. See if we can distinguish between how the minus sign is being used in this expression. So which minus sign represents subtraction? So we've got minus sign, minus sign, minus sign, minus sign, minus sign. Which ones represent subtraction? Also, which minus sign represents a negative sign? And which minus sign represents an opposite sign? Pause the video here and see if you could answer each of these three questions. First, we'll go through and see if we can identify these subtractions. Again, subtraction is a binary operation, so this is not subtraction. It's not taking place with another mathematical object. This is not. This is. You've got the difference of this expression with this expression. So this is a subtraction. This also is a subtraction here because you've got this whole big mess right here minus this whole big mess. So this is also a subtraction. And here you also have a subtraction because you've got the difference of this term with this term. So this is subtraction. Now we've got two of them left. This one here, we're talking about negative 2x, so that is a negative 2. So that is a negative sign there. But then as we saw in a previous slide, this expression right here may not actually be negative. So this is what we would consider an opposite sign. Again, you could technically call this sign a negative sign. However, we don't want to believe that that means it'll automatically give you a negative result. It could produce a positive result for specific values of x. So we've got the minus sign classified in those three different ways in this particular expression. Let's now use some other prerequisite knowledge we went over. We want to rewrite our expression, this expression here. We want to rewrite it with only addition. Of course, we're going to convert the subtraction to addition, not the opposite sign or the negative sign. So those are going to be there. The subtractions, though, are going to be converted to addition. So pause the video here and see if you can do that. So we've got that opposite sign out front, parentheses, negative 2x. We're subtracting a positive 1. That's equivalent to adding a negative 1. We're subtracting 3 times that quantity, so that's the same thing as adding negative 3 times that quantity. And in parentheses, you've got 5 minus 4x. That's the same thing as 5 plus negative 4x. These two expressions are equivalent to one another, except this one does not have any subtraction in it. And you will see shortly why we're so much more interested in addition than we are in subtraction. That leads us into a discussion of properties of the real number system. So that's where we need to go now. The properties we will look at will play a critical role in combining like terms. We can now begin to develop some of the properties of the real number system. We're going to look at 3 properties in particular. There are many, many more, and we will develop any other ones that we need throughout the course. However, for now, we want to specifically look at the property of commutativity, associativity, and the distributive properties. So those 3 different things. And don't forget our standard operations that we're talking about are addition, subtraction, multiplication, and division. And just a recall, because we're going to talk about properties of the real number system, real numbers are themselves those that can be written or approximated by a decimal. Property of commutativity. We want to figure out what operations are commutative. So for what operations can you flip the numbers, expressions around the operation and get the same result? Well, let's just explore. Let's take some numbers. Let's go first with addition. If you do 4 plus 8, you get 12. If you were to flip that around, 8 plus 4, you still get 12. Notice here that the order in which you add the numbers, whether you do 4 plus 8 or 8 plus 4, does not matter. You get 12 either way. And this is true actually with any real numbers. So addition is commutative since a plus b is always equal to b plus a for any real numbers a and b. So addition is a commutative operation. Let's see if there are any other ones. Let's look at subtraction now. Let's keep these same numbers. If you did 4 minus 8, you get negative 4. And if you did 8 minus 4, you get positive 4, which these are not exactly the same. So it matters the order in which you subtract things. You get a different result when you switch the order. So subtraction is not commutative. Let's check out multiplication. 4 times 8 is 32, and 8 times 4 is also 32. Now, in this case, we got the exact same thing, and this is actually true no matter what 2 real numbers we used. A times B is always the same thing as B times A. So multiplication is also a commutative operation. We've got 1 left. Let's check to see if division is commutative. We got 4 divided by 8 is 0.5, and 8 divided by 4 is 2. So as you can see, the order in which we do the division gives us a different result. So division is not a commutative operation. So we have 2 commutative operations in our real number system. They are addition and multiplication. That means that addition and multiplication are friendly in some ways. You are more flexible to do things with those two than you are with subtraction and division. Let's now take a look at the property of associativity. And what we want to do is see which of the four major operations are associative. For what operations can you do the computations in any order? So in this case, I'm not talking about flipping the order of the numbers around, actually doing a different operation first. So let's see what I mean by this. Let's use the numbers 2, 4, and 8, and we'll start with addition. If you wanted to find the sum 8 plus 4 plus 2, does it matter whether you do this addition first or this addition first? And what we're going to do to check is we're going to, in this first expression up here, we'll do the 8 plus 4 first, and in the second expression, we'll do the 4 plus 2 first. Up here, the 8 plus 4 gives us 12, and then we still have 12 plus the 2, which gives us 14. Down here, we're going to do the second sum first, the 4 plus 2. So we've got 8 plus the 4 plus 2 is 6, and then 8 plus 6 is also 14. Notice that we got the exact same thing. The order for which we did these computations, whether you do this computation first, this addition, or this addition first, you still get the same result. Now, this is actually true with any three real numbers, not just 8, 4, and 2. So addition is what we call associative because A plus B plus C is the same thing if you do the first addition first as if you do the second addition first. You get the exact same thing. So addition is associative. Let's see if any of the other operations are. Let's try subtraction. We'll use the same four numbers. If you had 8 minus 4 minus 2, does it matter if you do the first subtraction first or if you do the second subtraction first? Does it give you the same thing? Well, in the top expression here, 8 minus 4 gives us 4, and then 4 minus the 2 gives us 2. In the second expression, we do this 4 minus 2 first, which would give us 2. So we have 8 minus 2, and 8 minus 2 is 6. Notice we did not get the same result. What this means is if someone wrote down 8 minus 4 minus 2 exactly like that, you can't just do this 4 minus 2 first. It would give you a different result. So you need to follow the order of operation and do the subtraction from left to right. Whereas if you had 8 plus 4 plus 2, yes, the order of operations tell us to do the addition from left to right, but we already saw that even if you did the second addition first, you'd get the same thing. Whereas if we did the second subtraction first, we would not get the same thing. So subtraction is not an associative operation. Let's check to see if multiplication is. Using the same three numbers, we want to do 8 times 4 times 2, and we're going to do it twice. In the first one, we're going to do the 8 times 4 first, and the second one, we're going to do the 4 times 2 first. 8 times 4 in the top gives us 32. 32 times 2 is equal to 64. In the bottom one, we do the 4 times 2 first here, and we've got 8 times the new 8, and 8 times 8 gives you 64. Notice we get the same exact result, and that actually happens no matter what three numbers we're multiplying. So A times B times C is the same thing whether you do the A times B first or the B times C first. You get the same thing. So multiplication is what we call an associative operation. Let's check our last one. Is division associative? Again, we've got 8 divided by 4 divided by 2. We're going to do the same computation twice, except in the first one we do the 8 divided by 4 first, and the second one we'll do the 4 divided by 2 first. Up here, 8 divided by 4 gives us 2, and then we have 2 divided by 2 left, and 2 divided by 2 is exactly 1. Down here we do the 4 divided by 2 first. 4 divided by 2 is 2, and so we still have 8 divided by 2, which is 4. Notice we do not get the exact same thing here, therefore division is not an associative operation. So you cannot arbitrarily choose to do a second division first or a second subtraction first because those two operations, division and subtraction, are not associative, whereas addition and multiplication are. So what this ultimately means between addition and multiplication being both associative and commutative, you can move things around when you have one big product and it doesn't matter. With one big sum, you can also move things around however you like and do the computations, and you'll still get the result. You cannot do the same sort of thing with subtraction or division.